Here is your review for 1.6, which is photoelectron spectroscopy, or a lot of times we just refer to this as PES. So this is directly connected to the electron configurations. In fact, this is the evidence for how we know how many electrons are where they are. So what you need to be able to do is you need to be able to understand one of these graphs and interpret what element it is, and then in direct instruction in September we'll go through how you can predict how another element is going to compare. Alright, so first of all, I just love this image because this is the instrument that gives us the information. It kind of looks like a droid from Star Wars. Alright, so here's what we have for electron photospectroscopy. So again, photo means light. So what we're doing is we have an atom and they are sending energy at the atom. So if it's just light, we saw this in first year chem, when you put the electricity in or heat in, you can get different colors to come out of the atom because that comes from electrons moving around from one energy level to another, and then whenever an electron moves, energy is involved with that, and so energy is released. When we're talking about photoelectron spectroscopy, we are talking about using much higher levels of energy. So if you think back to the different electromagnetic waves that we've talked about, we've got visible light, which carries a certain amount of energy. UV light carries more energy, and then X-ray carries even more energy. So when we're using this, we are trying to get at the core electrons. So UV and visible, you're just going to deal with the electrons in the valence level. When you're talking about using PES, or specifically this type, we're going to send X-rays in, so they carry more energy, so we are more likely to get electrons out of the core levels or closer to the nucleus to be able to overcome that attraction and leave the atom. Alright, so here's just quickly, you don't need to be able to explain this, but I just think the instrumentation is it's just neat to see how we know what we know. So we've got a gaseous sample of atoms, bombard them with either X-ray or ultraviolet. As long as we know the amount of energy, then when we keep track of the photoelectrons that are ejected, we can measure the amount of energy, kinetic energy that they have. The difference between those two is the amount of energy it took to overcome the attraction. So we can figure out where the electrons in the atom are. Alright, so here's what a PES spectrum looks like. So on the x-axis we have what's called the binding energy. So the binding energy is the amount of energy in that attraction. Because again, whenever you have two magnets, I'm always going to keep going back to magnets. Opposite charges attract. Protons and electrons, or the nucleus and electrons, are like magnets. They are opposite in charge, so they're going to attract to each other. If you have two magnets that are stuck together, they're not just randomly going to become unattracted. In order to separate the magnets, you need to physically add your energy to it to separate the attraction, to overcome the attraction. The amount of energy it takes to do that is known as the binding energy. All right. And then we have the number of electrons on the y-axis. So sometimes these numbers will be there, sometimes they will not. Sometimes you will need to use your chemistry knowledge to infer what each of those lines represent, whether it's 1 or 2 or all the way to 6. So this one is for aluminum. Like I said, the binding energy is on the x-axis. It's also known as the ionization energy, and we'll talk more about that in September. But really it's just the amount of energy needed to overcome that attraction. So you'll notice that different than a lot of the graphs we work with, the highest levels are furthest to the left. So that means the first peak that you see right here, this is the highest binding energy, which means these are the electrons that were held the strongest to the nucleus. And on the far right side we have the lowest binding energy, which means that they feel the weakest attraction to the nucleus. And hopefully you're starting to connect, well, what does that mean about where they are in the atom? Alright, so again, the highest binding energy means it's going to be the most difficult to remove them, or it takes the most energy. Lowest, easiest to remove. Alright, now we connect that to the structure of the atom, and here we go. What we see now is this first peak is always going to be the electrons in the 1s. So assuming that we're not dealing with hydrogen, and only sometimes do we deal with hydrogen, whatever this peak is, this is the 1s2 peak. Then the next peak is going to be the 2s2, and then we have the 2p6, then we have the 3s2, then we have the 3p peak, and you'll notice this only goes up to the 1, so that's going to be 3p1. So again, this was aluminum. If you look at aluminum in the periodic table, it only has those 13 electrons. Its valence electron, or the outermost electron, the one that's easiest to remove is the 3p1. Okay, so our y-axis again is the number of electrons. I kind of went over that. So what you need to be able to do is, first of all, kind of the simplest thing is write the electron configuration from the PES, and that's really what I just did. We've got a 1s2, 2s2, 2p6, 3s2, 3p1. All right, and if you want to, you can just label them just like I did above the peaks. All right, so let's try that on this one. Okay, you notice that on the y-axis now, we don't even have any lines, but we still want you to interpret this. Again, always recognize this first peak is going to be the 1s2 peak, which means I now have a sense that, okay, this is 2, that makes sense to be 2, and that makes sense to be 2, and oh hey, actually I just noticed it on the other side, we have our 6 lines. But if you didn't, you could infer what those heights are. So I've got a 1s2, 2s2, 2p6, 3s2, and then 3p, and it only goes up to a 5. So my electron configuration, 1s2, 2s2, 2p6, 3s2, 3p5, and then I look at the periodic table, and this is chlorine. And we always assume these are in the ground state, and we'll talk more about ground state and an excited state. It's pretty simple. All right, and that's really that's the review from JV Chem. Again, this past year, if you are a junior, this year you also saw on the honors target the next part we're going to ask you to do, and so if you want to work on that on the homework, you can. If you are a senior, we did not do that with you when you were in chem, so that would be new, but you are welcome to go ahead and try that question on the homework. I will provide direct instruction for that in September.